Hello, my name is Andy Benson, and my partner is Patrick Flynn. And for our attack reproduction, we decided to break a RISC-V emulator written in C, and we used a fuzzer to discover the vulnerabilities. So first, how did we set up our system to attack an emulator? So to complete this attack, we used AFL++ to help us find a bug that we could then use to stage our attack. And AFL++ is an advanced open source fuzzer that has been used to find numerous bugs and vulnerabilities in a variety of programs. On the left is a diagram of the basic loop that AFL++ takes to find potential bugs. It first explores a piece of software with random inputs to try and maximize the number of edges it hits. These edges are places with jumps in logic. If a seed hits a new edge, it is deemed interesting and is fed back into the seed pool for further mutation. This is an attempt to reward productive seeds. The picture on the right is a screenshot of AFL++ running. This shows a variety of information about the execs per second, or how fast it is executing a program, the coverage metrics as percentages, and the number of interesting inputs. So, why is fuzzing effective? Fuzzing is an effective tactic for discovering bugs due to its unstructured nature. It has an uncanny ability to catch bugs that would have been missed by normal user testing, and it can be left alone for long periods of time to run. This makes it an ideal tool for attackers to passively probe different programs for vulnerabilities. Some drawbacks of fuzzers are that they struggle to explore new edges once they get, quote, stuck. This is because the random inputs might go down certain branches and never hit all the edges. Additionally, some fuzzers need very complicated harnesses to provide inputs into certain programs. Lastly, fuzzers normally have to run for a very long time on large open source programs to actually find bugs. This is because these programs are constantly monitored for bugs, making the jobs of fuzzers a lot harder. For this project, we wanted to attack a RISC-V emulator. We wanted to use an emulator written in C due to the variety of bugs that are present in most C programs regarding inputs, outputs, and strings. We assumed that this program would likely have vulnerabilities, especially considering it is a personal project. Additionally, we wanted to apply our code to a hardware-adjacent project to see how it would react to fuzzing. On the right, you can see that the RISC-V core we used is called RV. It is a personal project that currently has 614 stars on GitHub, which is quite a few stars for a RISC-V emulator. So now on to the implementation of how we found a bug to create our attack.
So the the fuzzing tended to turn up two main classes of bugs: floating point exceptions and segmentation faults. Floating point exceptions are when the division hardware is used, and more specifically, when you give one of the operands an invalid input, which in this case would be division by 0. And in our example that we provide on the slide, the remu instruction would throw this error. Segmentation faults are another common fault in programs like this. In our particular emulator, these are often thrown by invalid inputs to the load and store instructions and to the branch and jump instructions. So C does not have a way to really catch and handle exceptions. So the only way to catch exceptions is by utilizing operating system libraries. And in this case, we use the signal function, which allows you to specify which exceptions that you want to catch and how you wish to handle them. In our example, we caught the segmentation fault in the floating point instructions, and we also catch the interrupt signal, but we will explain that later. So one of the ways that the signal handlers can be used to do malicious activity is to launch a shell. And this can be very dangerous to a system because once you launch the shell, even if you are in a limited environment, you can still do a lot of damage to the underlying system. And this breaks, the core confidentiality, integrity, and availability principles. The shell allows you to bypass what the original purpose of the program was and to do all kinds of arbitrary things.
So once we created our attack and found our bugs, we alerted the creator of RV of the potential bugs. And we mostly just focused on the invalid instructions that incorrectly hit part of the ALU with the REMU operation. And this is because this was the most direct bug that we could actually fix, unlike the segmentation faults from improper jumps. If we loaded a register, there's only so much that we could actually do unless he rebuilt parts of the core to monitor jump locations. So this was the first issue that we actually brought up. And these bugs are unlikely to have any effect in the real world, but if someone was hosting this program somewhere and allowed users to add their own harnesses to run the emulator, then this attack might be able to breach a different system. And also, this attack could come up if someone was arbitrarily trying to jump to memory locations instead of using the signal handler harness. And that would be a much more difficult attack, but it could be possible. So now on to some of the technical challenges. Other than setting up AFL++, which can be a challenge on its own, creating the harness was the most difficult part for this. So this program would crash frequently due to improper handling of inputs from AFL++, and this is because AFL++ uses a variety of inputs that are not actually ASCII values. These would get read by the program and proceed to crash the harness before the inputs could even be given to the core. To fix this problem, we had to further sanitize our inputs by converting all the input information into valid ASCII characters and then extracting the 32-bits of hex values that could be passed into our core as specific RISC-V instructions. And this is what we used during our final runs with AFL++ to actually find our bugs. So now on to a quick demonstration. So as you can see on my screen here, I have this command up. This will just go and run a simple AFL++ iteration. So I will run it, and then you can see right here, the coverage that we have is increasing. Here is basically the number of interesting inputs that we have. Up here is how long it is running. And then this is how many executions or execs we have per second. And so as you can see, there are no bugs being found currently. And this is fine because this is actually the version that we were running with no bugs because we had actually handled stuff in our harness. So if I would stop this and go and show you this version, so this RV debug was actually the original version of the harness with the signal handlers. And for the input crash, input 1, this is an input that is an invalid RISC-V instruction. So as you can see here, you can see the instruction that caused it to break is this 0F007F33. So this is not a valid RISC-V instruction, but as you can see, it's set so that both two registers are set to be 0. And this just happens to fall into the ALU and then go and hit the REMU instruction. And as you saw on the previous slide, the REMU instruction is just A mod B. So if we do 0 mod 0, that will just crash the program and give us the floating point exception. And then at that point, we will have a shell. So you can go and move around to different places and do different things. So you can see it works normally. So that's just a very quick demo. And you can see the fuzzer was used basically to find the specific inputs that we used here and identified instructions like this that would either hit the floating point exception or the segfault exception. And that would occur from loading invalid memory locations into a register and then trying to jump to that location.
All right, so now on to the discussion. So what are the broader lessons that we could take from this? The first one is kind of the most basic thing that you can do is input sanitization. And as much as possible, you should always check your inputs before you run them within any program. As a further extension to this, like the next thing you want to build off of is air handling. So, when a program is running, especially if it's exposed as a library or something you can give input to, you want to capture all possible exceptions to make sure you can handle any undefined state. And as an extension to that, you want to make sure that you're monitoring the state of your program. Especially if you can't do much in terms of input sanitization, you want to make sure your program is not really interacting with the outside environment more than it should be. And with that is the system events. If you're doing stuff that's outside what your program would expect, then you likely have a problem. And then in terms of the defenses, again, you want to check your input. In our case, there's not really much that we could do with this since we're running binary code. The most that we could do is check things like memory addresses before they go to memory, and check jump locations to make sure we're not jumping beyond the bounds of memory. You can also possibly do things like checking the opcode and make sure you have a valid instruction, but it kind of depends ultimately what you're using this tool for. But what you can do as a defense is to catch errors. So in our case, make sure the signal handlers are already implemented, and they will do things to keep your program in a state that you would expect. And building on that, you want to maintain a defined state. So ideally, your program doesn't crash and throw errors, but you want to have an idea that if that does happen, what state should your program be? Should it start over? Should it gracefully exit? You want to have an idea of that and make sure the signal handlers act accordingly. And then finally, you want to make sure the underlying system is secure, because sometimes, even though we try our best to secure our applications, vulnerabilities are found, whether in our application or the libraries we use or whatever. So we want to make sure that the underlying system is secure as possible. So if you do get out of the program, damage is minimized.
Right. And that's everything. So thank you for listening to our presentation.